Today we will solve some examples in section 3.3. Example 1. Find where the function f of x is increasing and where it is decreasing. So we can use the increasing and decreasing test, or another name of this theorem is monotonicity test. So we find the derivative of this function, power rule 12x cubed minus 12x squared minus 24x. We factor this polynomial 12x x squared minus x minus 2. Okay, factor this. So we apply the increasing and decreasing test. X. If x equals 0 or minus 1 or 2, then f prime of x is 0. If x is greater than 2, then x minus 2 is positive. X minus 0 is positive, and x minus 1, that is x plus 1, is positive. And the exponents here are all 1, are all odd numbers. So plus, minus, plus, minus. According to the increasing, decreasing test, on this interval, the function is decreasing, increasing, decreasing, and increasing. So the answer is f is increasing on some intervals on these two intervals. This interval is minus 1, 0. Of course, and all its subintervals. For example, you can use open interval or minus 1 to minus 1/2. But here we use the maximal interval. Okay. And on this interval, 2 to infinity, f is decreasing on minus infinity to minus 1, and this finite closed interval 0, 2. Okay, this is example one. Example two. Find the local minimum and the maximum values of the function f in example one. Okay, here we will use the first derivative test. First derivative test, because the derivative of f at -1 is 0, at 0 is 0, at 2 is 0. Therefore, this function has three critical numbers, -1, 0, and 2. Because f is differentiable, f is continuous on these 3 points, at these 3 points. So, decreasing, increasing, the sign of f prime changes from minus to positive, means f of -1 is a local minimum. Here, increasing and decreasing, this is a local maximum. This number is a local minimum. So, all we have to do is to find the values of f at these three numbers. At -1, this is 3 plus 4, 7, minus 12, minus 7. Sorry, 7 minus 3, minus 5 plus 5 is 0. At 0, if x is 0, then the value of f of 0 is the constant, term, 5. 2. 3 times 16, 48. 48. 48. 8, 4. 32. 48, 32. 16. 16 minus 48. Okay. Minus 48. This is 48 cancel. So minus 32 plus 5 minus 27. Therefore, local, this is local minimum. Local minimum, and this is local maximum. Zero and the minus 27. So this is the first derivative test for local extreme values. Next, about the concavity. sketch a possible graph of a function f that satisfies the following conditions. Okay, sketch a possible graph of the function f satisfying the following three conditions. Of course, you can sketch the graph directly by obeying this information, but I prefer to make a table. Here, the numbers one main concern is 0, 2, and 4. 0, 4. So 0, 2, and 4. The information for first derivative at 0 and 4, whose values are 0. And between 0 and 4, the first derivative is positive. Positive, positive. Though we don't know the exact value of f prime of 2, but we still know this one is positive. F double prime, the second order derivative of the function f. If x is less than 2, this is positive. If f is greater than 2, then this is negative. Also, for the first derivative, if x is less than 0 or x is greater than 4, the sign is minus. Minus. At 2, we don't know. But this is not important. The behavior of the function f. Okay. Increasing. 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 Maybe. Okay, we use this and the decreasing. Second derivative is positive, means concave upward. concave upward, concave downward, downward. Therefore, the behavior of f should be in this part, this is decreasing and this is increasing. So decreasing and then concave up means the left part of this curve. And the derivative is 0. Okay, increasing. So the right part of this curve. Then increasing. So the left part of this curve. And decreasing. So you almost can guess the behavior of this function. And at 0, the value is 0. At 2, the value of the function f is 3. At 4, the value is 6. Usually we omit this part by decreasing and the concave up means the left part. Increasing and concave up means the right part.